Hi guys, my name is Robinson George Adishil, and this is an update on Null32, a custom operating system I've been building from scratch for the ESP32. It uses no standard libraries, no Arduino framework, it's just bare metal C and assembly talking directly to the hardware. Now, this is the third milestone, and the short version of what happened is, for the first time, this kernel loaded a separate program from disk, actually ran it as real compiled code and not a script. A quick recap on where I left off last time. By milestone 2, the OS could boot itself properly, jump into instruction memory through a handwritten trampoline, and it could read files off an SD card through a FAT32 driver I wrote myself. But here's the thing, when I said run a program back then, I meant something pretty limited. The program was just a text file. My kernel would read it line by line, match strings like high pin 25 or low pin 25, and just flip a GPI open. That was it. It's basically a tiny scripting language, not an operating system running software. And it had three real limitations. The first one, obviously, being no compiled code. I couldn't run anything written in C, only these interpreted strings. The second one, it had no memory isolation. Nothing was actually tracking which memory belonged to what, and there was no way to protect the kernel from the program stepping on it. And lastly, I had already written or designed a real executable file called an NXE or Null32 executable, but it only existed on paper. I had the specification, but no code could actually load one. Now, this milestone was about actually closing that gap, actually building the four systems that you need to load and run in real binary safely. First, we needed a paged memory manager, a way to hand out fixed size chunks of memory to programs and take them back when they're done. Second, we need an actual tool chain, meaning I had to write a C program completely separately from the OS, compile it on its own, and then pack it into my custom executable format. Third, we need a relocating loader, because when a kernel copies that program into memory, it has to fix up all of that program's internal pointers, since the program has no idea in advance where it'll end up. And fourth, we need a safe context switch, the actual moment where the kernel hands the CPU over to the code it didn't write and has to reliably get it back. Now let's start with memory. Every program's code and data now lives in a fixed 4 kilobyte pages, 24 pages of instruction memory, and 32 pages for data. The main reason we have to use separate memory instruction and data memory is because of the way that ESP32 is designed. We have two separate memories called the IRAM and the DRAM. And the DRAM cannot exist in the IRAM, and the IRAM cannot exist in the DRAM. The data and memory is kept separate. The kernel reserves whatever pages it needs for itself first, and everything else gets tracked in the bitmask. So a number that where each bit says whether a page is free or taken. Now, when a program needs memory, the allocator walks that bitmask, finds the first free bit, flips it to use, and hands that page to the program. When the program finishes freeing its memory, it just clears the bits it was using. Nothing more, nothing less. It's a simple idea, but it's the foundation everything else this milestone depends on. Now, let's look at the full journey a program takes. It starts with a main.c file, a real C file, that gets compiled offline into an L file, the standard compiler output, cross-built for the ESP32's extensive architecture. Then a Packer script I wrote strips that ELF file into a custom .nxe format. Just the code, the data, and a table of relocations. That file gets copied onto the SD card like any other file. Everything up to that point happens once, on my computer before the board ever boots. Everything after this dash line happens live on the ESP32 itself. The kernel load function reads that file, allocates pages where, copies it in, and patches its pointers. Then a second function actually launches it. One detail worth calling out is that my custom linker script places the program's code at address 0 and its data at a very high address when it's compiled. Neither of those addresses are real. The program will actually load somewhere completely different. That gap just gives the loader a unmistakable way to say, hey, this pointer's to code and this pointer's to data. The next pillar is for relocation. When the C program gets compiled, the compiler has no idea of where the physical page of memory it's going to end up in, and that's decided later at runtime, but whatever pages happens to be free at the moment. So every single pointer inside the program has to be rewritten after it's copied. As it's compiled, a call to printf just points to somewhere inside the code, and a reference to a string that points to a fake placeholder address, with like the previous really high address plus some offset. My loader reads the relocation table that lists every single one of these spots, patches them. The code program gets the program's real starting address added to it. data pointer gets remapped from the placeholder into whatever the program's actual data page landed. After that, every pointer in the program touches to resolve to the memory that the kernel actually gave it, and nothing else. And this was the moment I was actually most stressful about, the context switch. The kernel is about to jump into memory that it has just finished writing, hand over the CPU to code it didn't write, and needs to get back control later. It's a five-step handoff. First, we have to save the kernel's current stack pointer. Second, we have to load in the user's private stack pointer. We have to jump into the program. So a single instruction called callx0 transfers control into the program. Fourth, we need to run that program. The program executes freely using its registers however it wants. And lastly, we need to restore. So when the program returns, the kernel needs to reload its own stack pointer and pick up exactly where it left off. And the first step matters more than it sounds like. Why not just keep the kernel stack pointer in a register? Because the guest program and everything it calls back into is completely free to overwrite any register the compiler considers safe to clobber. If I'd kept that address in a register, it could be silently destroyed. Spilling it into fixed memory actually allows the stack pointer to survive no matter what the guest code does. And I actually want to talk about a bug here because I think the fix is more interesting than everything that I just worked. User programs need to call back into the kernel, where something as simple as printf will actually being directly linked to it. My first attempt at that bridge used a hard-coded memory address where I had hand-measured the kernel's system call table and then linked the actual address. The problem with that was that it was only correct for one specific build. The moment I had changed anything else in the kernel, like adding a new buffer size or updating the buffer size, adding a new global variable, that table would silently shift into a different address. And the hard-coded pointer would now be wrong, and the user's printf program would jump into garbage memory. There would be no crash, no error message, just silence. And it's really hard to diagnose. And the fix was to stop hard coding it. Now, at boot, the kernel writes a pointer to wherever its system call table it actually ended up using one fixed mailbox address. User code just follows that pointer instead of assuming a location. The table's real position can move freely from build to build, and the link between them. Okay, and here is a quick demonstration on the program executing. So here we have int a, we initialize it to 5, int b, 10, and we set csb plus a. We can print a hello from program. We're going to print like a, b, c, d. So we're going to print like the equation itself, and we're going to return. Now here we're just declaring what permissions we need. So in this milestone, we don't actually check what we need, and this is the SDK, which allows us to develop this application and actually link it. So we can actually use the make file to actually clean, and we can actually build it. So we can actually see the code, the data, and we can see the number of reload allocation tables. So this is like the entries here, where it's pointing to, and lastly, it's 156 bytes. So we actually have the file. So now let's reveal it. We're going to get a programs.nxe. So if I reveal in File Explorer, we see the entire build. And now we actually have to transfer this to the SD card. So if I connect the SD card, it should boot up any second now. Currently, the SD card only contains two things, the programs and the null32. And we can actually replace the file here. And now let's just create one more program for a quick demonstration to prove that it actually works. Let's just do printf. Let's say this is the third milestone, stone, new line, and let's add a new line in the back just in case. Obviously, we have to have proper syntax, so semicolon, and let's compile it. Clean, we're going to build it, and we can see that it has one allocation or one relocation, so from here, and it's smaller. So we can go here. Let's rename this to programs 2, or let's name this 2. Let's copy it here and move it to the thing. So let's eject it, and let's go back to your Arduino. Or the serial monitor, which allows us to communicate. So we're going to restart or reset the ESP32. We're loaded in. Let's run NXE. So first program we're going to run is programs.nxe. And let's see Right here, we have hello from program, 5 plus 10 is equal to 15, and we're returning. So we transfer the control over to the program, execute it, and we return. Now let's execute the second program, 2.nxt. And see, we're reading it, we're executing it, and we're returning it. And we can continuously execute these programs and return it. And yeah, that is the third milestone. Next, I would like to actually implement process scheduling, so multiple programs can run without one having to finish before another starts. I'd love to enforce hardware permissions that the programs are declared in the header, so a program only uses what it needs. Right now, the kernel just simply reads them but doesn't act on them yet. I'd like to implement real interrupts and system call traps instead of just one hard-coded printf hook I'm using today. And I'm still have that bug that I'm carrying over from the last milestone, which is the FAT32 driver still having the issue in how it handles file name capitalization. And that's milestone 3. Thanks for following along. Until next time.